At the smallest scales, the universe evolves through precise physical states, each one carrying a complete record of what exists at that moment. Imagine a system frozen in time, every particle located somewhere, every motion defined, every interaction encoded in a mathematical description. That full description is what physics calls information. It does not involve meaning, interpretation, or awareness. It is a statement about how completely the physical state of a system has been specified. In classical physics, information lives in phase space. Phase space is an abstract mathematical arena where every possible state of a system occupies a unique point. For a single particle moving through ordinary space, 3 coordinates describe its position and 3 additional numbers describe its momentum. Together, these 6 values define one exact microstate. A system containing many particles expands this description into a space of enormous dimensionality, yet the logic remains unchanged. Each exact configuration corresponds to one precise location in phase space, and that location represents the system's full information content. Classical laws of motion move points through phase space along smooth trajectories. As time passes, the system flows from one microstate to another, tracing a continuous path. The equations governing this motion preserve structure. Phase space volumes deform, stretch, and fold, yet they retain their total size. This property, formalized through Liouville's theorem, expresses a deep principle. Classical dynamics preserves information. Every microstate remains distinct from every other. Knowing the exact present state allows the exact past and future to be reconstructed in principle. Macroscopic physics introduces a different language. Temperature, pressure, density, and entropy describe systems with vast numbers of microscopic constituents. These quantities define macrostates. Each macrostate corresponds to many microstates, often an astronomically large number. Entropy measures how many microscopic configurations fit within a given macroscopic description. When entropy increases, the system explores a larger region of phase space compatible with its macroscopic constraints. The underlying microstates continue to evolve deterministically, yet observers choose to ignore nearly all of that detail. From this perspective, classical irreversibility arises from coarse graining. Practical descriptions discard microscopic distinctions and track only averaged properties. Information remains present in the full phase space description, even as it becomes inaccessible to macroscopic observation. Classical physics therefore treats information as conserved, with apparent loss arising from limited resolution rather than fundamental law. Quantum mechanics reshapes this picture while strengthening its core principle. A quantum system does not occupy a point in phase space. Instead, it is described by a state vector residing in Hilbert space, an abstract mathematical structure whose dimensions correspond to all possible configurations of the system. This state encodes probability amplitudes rather than definite positions and momenta. Superposition allows multiple possibilities to coexist within a single quantum state linked through precise mathematical relationships. Despite this unfamiliar structure, quantum theory enforces an even stricter form of information preservation. The time evolution of a closed quantum system proceeds through unitary transformations. Unitarity ensures that the total probability remains exactly conserved and that the inner products between quantum states remain unchanged over time. Distinct states remain distinct as the system evolves. The mathematical map between past and future states remains one-to-one. This one-to-one correspondence carries a crucial implication. Unitary evolution is reversible. Every allowed transformation possesses an inverse. If the exact quantum state at some moment is known, the state at any earlier time can be reconstructed by applying the inverse evolution. This reversibility exists at the level of fundamental law, independent of practical limitations. Complexity may render reconstruction infeasible, yet the underlying mapping remains intact. Quantum information therefore behaves as a conserved quantity. When systems interact, information flows between them rather than disappearing. Entanglement plays a central role in this process. As two systems interact, their joint quantum state encodes correlations that exceed any classical description. Information becomes distributed across these correlations, stored in relationships rather than localized properties. Subsystems appear to lose information when examined in isolation, yet the combined system retains a complete record. The measurement process illustrates this redistribution. When a quantum system interacts with a measuring device, their states become entangled. The combined system then interacts with the surrounding environment, spreading correlations further. From the viewpoint of the full quantum state, evolution proceeds smoothly and deterministically. Apparent randomness arises when observers describe only a small fraction of the total system and ignore the rest. Information remains encoded in the global state. Unitarity serves as a structural pillar of quantum theory. It guarantees probability conservation, consistency of predictions, and the ability to relate experimental outcomes across time. Without unitarity, quantum mechanics would lose its internal coherence. Distinct preparation procedures could converge onto identical outcomes, erasing the link between cause and effect. Predictive power would dissolve, and the framework would fail to support experimental science. Because of this, quantum theory places strict limits on what physical processes can do. A process that truly erases information would collapse multiple distinct initial states into the same final state. Such behavior contradicts unitary evolution. Any theory permitting fundamental information destruction must alter quantum mechanics at a foundational level or abandon it altogether. This requirement elevates information conservation to the same status as energy conservation. It becomes a defining constraint on allowable physical laws. While energy conservation arises from time translation symmetry, information conservation arises from the mathematical structure of quantum dynamics itself. The two principles operate independently, yet jointly shape the behavior of the universe. At ordinary scales, this framework operates quietly in the background. Chemical reactions, nuclear decays, and atomic transitions all respect unitarity at the microscopic level. Even in complex systems where thermalization occurs and entropy grows, the underlying quantum evolution preserves the full information content. What changes is accessibility, distribution, and complexity, not existence. This perspective frames the central tension that arises when gravity enters the story. General relativity describes space-time geometry and predicts regions where classical trajectories terminate at singularities. Black holes introduce horizons that hide internal structure from external observers. Classical descriptions compress rich detail into a few global parameters. Quantum mechanics demands that every distinction remains encoded somewhere in the physical state. The question then emerges naturally. When matter collapses behind an event horizon, where does its information reside? If radiation later carries energy away, what structure does that radiation encode? These questions acquire urgency because information conservation stands at the core of quantum theory. Any process that appears to erase information challenges the consistency of the framework itself. The information paradox begins here, grounded in definitions rather than speculation. Information represents the full specification of physical states. Classical and quantum physics both preserve it at the fundamental level. Quantum mechanics elevates this preservation into a rigid mathematical requirement through unitarity and reversibility. Within this structure, forgetting lacks a physical mechanism. The universe may scramble, redistribute, and conceal information within vast webs of entanglement, yet its laws demand that the record endures. A region of space-time collapses inward under its own gravity, and the geometry itself reshapes to form a boundary that light cannot outrun. From the outside, this boundary appears quiet and sharply defined. From within the mathematics of general relativity, it marks a profound division between what can influence the future of the universe and what remains sealed away. This boundary is known as the event horizon, and it defines the essential character of a black hole. The event horizon functions as a causal surface. Events that occur outside it can send signals outward and affect distant observers. Events that occur inside it influence only the interior. The horizon does not act as a material surface. It has no thickness, no texture, and no physical substance. Instead, it arises purely from space-time geometry. At the horizon, the paths that light can follow tip inward, so that every future-directed trajectory leads deeper into the gravitational well. This causal structure gives black holes their defining observational feature. Matter, radiation, and information cross the horizon and cease to produce any direct influence on the external universe. From the perspective of a distant observer, infalling objects appear to slow and fade as they approach the horizon, their signals redshifted by the intense gravitational field. The horizon itself remains a silent geometric boundary, encoding the point beyond which influence ends. Within classical general relativity, black holes emerge as exact solutions to Einstein's field equations. These solutions describe regions where gravity dominates completely, shaping space-time into a form that funnels matter inward. The simplest of these solutions describes a non-rotating, uncharged black hole. More general solutions allow for rotation and electric charge. Despite the complexity of the matter that may have collapsed to form them, the final space-time geometry settles into a remarkably simple form. This simplicity is formalized by the no-hair theorem. According to this principle, stationary black holes are fully characterized by just three externally measurable parameters: mass, electric charge, and angular momentum. Every other detail of the matter that formed the black hole, including chemical composition, internal structure, and multipole moments beyond these three quantities, fails to appear in the exterior gravitational field once equilibrium is reached. The no-hair theorem expresses a kind of universality. Two black holes with the same mass, charge, and angular momentum share identical external geometries, regardless of how different their formation histories may have been. A black hole formed from a collapsing star, and one formed from the merger of compact objects present the same space-time structure if these three parameters match. The exterior space-time carries no imprint of the internal complexity that preceded collapse. From a classical standpoint, this behavior aligns naturally with the causal role of the event horizon. Information about infalling matter continues to exist within the interior space-time, yet causal structure prevents that information from influencing the exterior. The loss of observable detail does not imply destruction within classical theory. It reflects a limitation on what external observers can access. Classical determinism remains intact in this picture. General relativity supplies well-defined equations governing space-time evolution. Given complete initial data on a suitable surface, the future geometry follows uniquely. The interior of the black hole evolves according to these same laws, even though its details remain hidden from outside view. Information persists within the space-time description, even as observational access narrows. From the outside, however, black holes behave as perfect absorbers. Matter falls inward, energy contributes to the mass, angular momentum may change, and electric charge accumulates or neutralizes. Beyond these global quantities, external measurements reveal nothing further. Radiation emitted during collapse fades, and the black hole settles into a stationary state that appears remarkably featureless. This featurelessness carries a thermodynamic echo. As matter falls in, entropy associated with the external universe changes. The black hole itself acquires properties resembling those of a thermodynamic system. Its mass relates to energy, its surface gravity to temperature, and its horizon area to entropy. These relationships emerge within classical general relativity through analogies that later gained deeper significance. Yet, within the classical framework alone, the picture remains internally consistent. Information about infalling matter resides within the interior spacetime. The horizon marks a boundary of influence, not of existence. Classical observers outside the black hole encounter an effective loss of detail, while the full spacetime description retains it. Quantum theory reframes the situation in a way that sharpens the tension. Quantum mechanics treats information as inseparable from physical state evolution. States evolve through unitary transformations that preserve distinctions between initial configurations. When quantum fields interact with gravity, especially near horizons, the question of how information flows becomes unavoidable. From a quantum perspective, matter falling toward a black hole carries quantum states defined by wave functions or quantum fields. As these states approach the horizon, their evolution remains governed by quantum dynamics. The horizon introduces extreme gravitational redshifts and time dilation, altering how processes unfold relative to distant observers. The quantum state becomes increasingly entangled with degrees of freedom near the horizon. If black holes function as perfect absorbers in the quantum sense, the implications run deeper than classical inaccessibility. Quantum determinism requires that the mapping between initial and final states remains one-to-one. A system that absorbs quantum states and later emits radiation, lacking any trace of those distinctions, would break this requirement. The no-hair simplicity that appears so natural classically begins to look problematic under quantum scrutiny. The apparent conflict arises because classical black holes compress vast complexity into a few parameters, while quantum mechanics demands that complexity remain encoded somewhere within the physical description. The horizon, which serves as a causal boundary in classical spacetime, becomes a focal point for this conflict. Does information cross the horizon and remain encoded within interior degrees of freedom, forever inaccessible yet preserved? Or does the horizon itself acquire microscopic structure capable of storing and processing quantum information? Classical general relativity offers no guidance on this question. It treats the horizon as a smooth geometric surface without internal degrees of freedom. Quantum field theory in curved spacetime initially followed this classical intuition, treating the horizon as passive. Early calculations focused on how quantum fields behave near horizons without modifying the underlying spacetime structure. Within this semi-classical picture, black holes appear to erase distinguishing features of quantum states from the viewpoint of external observers. Infalling matter alters only mass, charge, and angular momentum. Any further distinctions vanish from observable quantities. This behavior stands in direct tension with the quantum principle that physical evolution preserves the full information content of states. The conflict sharpens when one considers evaporation. If a black hole absorbs matter, settles into a simple stationary state, and later radiates energy away, the final state of the universe appears simpler than the initial one. The external radiation seems unable to encode the vast diversity of possible infalling configurations. The black hole appears to act as a sink that swallows detail and returns only coarse-grained output. This tension does not arise from speculation or philosophical preference. It emerges from placing two successful theories side by side. General relativity describes black holes as simple objects defined by global charges. Quantum mechanics describes physical systems as information-preserving entities whose evolution remains reversible at the fundamental level. The event horizon sits at the intersection of these principles. The description of black holes as perfect absorbers therefore carries more than observational meaning. It defines the point where classical spacetime geometry and quantum information theory intersect. The horizon enforces causal separation, while quantum mechanics enforces information conservation. Reconciling these principles requires understanding whether the simplicity of black holes is fundamental or only apparent. This question reshapes how black holes are understood. They transform from astrophysical curiosities into theoretical laboratories. Their horizons become arenas where space-time, quantum fields, and information theory converge. The classical picture offers clarity and elegance, yet it leaves unanswered how quantum states survive passage into regions sealed by geometry. The stage is now set for the paradox to fully emerge. Black holes appear to absorb everything while revealing almost nothing. Classical theory embraces this simplicity. Quantum theory demands a deeper accounting. The resolution of this tension lies ahead as the behavior of horizons under quantum laws comes into focus. Long before quantum effects entered the discussion, black holes had already begun to disturb the clean boundaries between gravity and thermodynamics. This disturbance emerged quietly from mathematics rather than observation, through a set of unexpected parallels between the behavior of black holes and the laws governing heat, work, and entropy. In classical general relativity, black holes obey a collection of precise mathematical relationships known as the laws of black hole mechanics. These laws arise directly from Einstein's field equations and the geometry of event horizons. At first glance, they appear as formal identities describing how mass, surface gravity, angular momentum, and horizon area change under physical processes. Yet their structure mirrors the familiar laws of thermodynamics with striking fidelity. The first law of black hole mechanics relates changes in a black hole's mass to changes in its surface gravity, horizon area, angular momentum, and electric charge. The form of this relationship closely resembles the first law of thermodynamics, which relates changes in energy to work and heat. Surface gravity plays a role analogous to temperature, while horizon area plays a role analogous to entropy. This resemblance emerges naturally from the equations, without interpretive embellishment. The second law of black hole mechanics introduces an even more provocative statement. In any classical process consistent with general relativity, the total area of black hole event horizons never decreases. Horizons can stretch, merge, and grow, yet their combined area remains non-shrinking. This result, known as the area theorem, follows from the causal structure of spacetime and the behavior of null geodesics under reasonable physical assumptions about matter. The area theorem establishes a form of irreversibility within classical gravity. Processes involving black holes display a preferred direction in time. Matter falls in, horizons expand, and the geometry evolves toward larger horizon areas. This echoes the second law of thermodynamics, where entropy increases over time for closed systems. The resemblance becomes difficult to dismiss as coincidence. Despite this parallel, classical general relativity initially treated it as formal rather than physical. Horizon area appeared to behave like entropy, yet black holes were assumed to have zero temperature. Without temperature, entropy lacked operational meaning. A system at zero temperature could carry entropy mathematically, but it would not exchange heat or radiate. The analogy remained incomplete. This uneasy situation changed when entropy was taken seriously as a physical quantity rather than a formal placeholder. Entropy measures the number of microscopic configurations compatible with a macroscopic description. In statistical mechanics, entropy reflects hidden degrees of freedom, unseen but real. A system with entropy possesses microstates that are not captured by its macroscopic variables. The application of this idea to black holes marked a decisive shift. If horizon area behaved like entropy, then black holes might possess microscopic degrees of freedom. These degrees of freedom would remain invisible to classical observation, yet they would contribute to a genuine thermodynamic entropy. This step was taken by Jacob Bekenstein, who proposed that black holes should be assigned an entropy proportional to the area of their event horizons. His reasoning followed from thought experiments that combined gravity, thermodynamics, and quantum principles. When matter-carrying entropy falls into a black hole, that entropy appears to vanish from the external universe. If black holes carried no entropy of their own, the total entropy outside would decrease, violating the second law of thermodynamics. To preserve the universality of the second law, Bekenstein argued that black holes must themselves possess entropy, increasing as matter falls in. The simplest and most natural candidate for this entropy was the horizon area. Area grows monotonically in classical processes, matching the expected behavior of entropy. The proportionality between entropy and area introduced a new physical interpretation of black hole horizons. This proposal challenged classical intuition at a fundamental level. Entropy traditionally scales with volume, reflecting the number of microscopic constituents in a system. A gas confined within a box carries entropy proportional to the number of particles and the volume they occupy. A black hole, by contrast, would carry entropy proportional to its surface area, not its interior volume. This inversion hinted at a deeper restructuring of physical principles. It suggested that the fundamental degrees of freedom associated with gravity might reside on boundaries rather than in bulk regions of space. At the time, this implication remained speculative, yet the area-entropy connection alone carried profound consequences. Entropy implies hidden microstates. This statement holds across all of statistical physics. Whenever a system has entropy, it admits multiple microscopic configurations consistent with the same macroscopic appearance. A cup of hot coffee looks the same macroscopically across countless molecular arrangements. Entropy counts those arrangements. Applying this logic to black holes leads to an unavoidable conclusion. If a black hole has entropy proportional to its horizon area, then it must possess a vast number of microscopic configurations that all produce the same macroscopic geometry. The no-hair simplicity of black holes would then reflect a coarse-grained description, hiding enormous internal complexity. This idea strains classical general relativity. The classical theory assigns no microscopic degrees of freedom to the horizon. The geometry appears smooth and featureless. There is no place within the equations for an exponential number of microstates. The entropy area relation therefore introduces the first clear fracture in the classical picture. The area theorem reinforces this fracture by encoding irreversibility directly into spacetime geometry. Classical gravity predicts that horizons grow in one temporal direction. Thermodynamics predicts that entropy grows in one temporal direction. The parallel suggests that gravitational dynamics already contain a statistical arrow of time. That arrow demands an underlying ensemble of microstates. Within classical physics, irreversibility usually arises from coarse graining. Fundamental equations remain reversible, while entropy increase reflects ignorance of microscopic detail. The area theorem, however, emerges directly from the field equations themselves. It does not depend on averaging or statistical assumptions. This difference deepens the puzzle. If black hole entropy behaves like ordinary entropy, then the horizon area increase reflects transitions between microscopic configurations. Yet classical theory offers no account of those configurations. The horizon becomes a macroscopic thermodynamic object without microscopic explanation. This tension sharpened further when thought experiments involving information were considered. Suppose matter with known quantum states falls into a black hole. The horizon area increases in a way that reflects added entropy, yet the external description loses track of the detailed state. The entropy increase suggests that information has been absorbed into microscopic degrees of freedom associated with the horizon. At this stage, the classical view still permitted a conservative interpretation. Information could reside within the black hole interior, hidden behind the horizon, but preserved within space-time. Entropy would then reflect inaccessible detail rather than destruction. The horizon would act as a bookkeeping surface rather than a physical storage medium. Even this interpretation carries weighty implications. It requires that the black hole interior encode a vast number of quantum states. It requires that horizon area track that information content precisely. The smoothness of the classical horizon would then mask a deep underlying structure, invisible at macroscopic scales. The analogy between black hole mechanics and thermodynamics therefore marks a turning point. It transforms black holes from purely geometric objects into thermodynamic systems. It elevates horizon area from a geometric quantity to a measure of physical entropy. It demands microscopic interpretation where none previously existed. This realization did not resolve the information problem. Instead, it sharpened it. Entropy provides a quantitative measure of missing information. Assigning entropy to black holes forces the question of where that information resides and how it evolves. The classical framework supplies no answer. The first crack in classical thinking appears here. Gravity begins to display thermodynamic behavior. Geometry begins to encode entropy. Horizons begin to resemble statistical systems rather than passive boundaries. These insights prepare the ground for a deeper transformation, one that arrives when quantum effects near horizons are taken seriously. From this point onward, black holes no longer appear as inert sinks defined only by mass, charge, and spin. They become thermodynamic entities whose simplicity conceals enormous complexity. The demand to explain that complexity drives the information paradox forward, drawing quantum mechanics and gravity into direct confrontation. Near an event horizon, space-time bends so strongly that the usual distinction between empty space and matter begins to blur. In this region, gravity reshapes the behavior of quantum fields themselves. The result emerges from combining two well-tested frameworks: quantum field theory and general relativity. When quantum fields propagate through curved spacetime, their behavior departs subtly yet decisively from what flat space intuition suggests. Quantum field theory describes particles as excitations of underlying fields that permeate all of spacetime. Even in regions devoid of matter, these fields remain active. Their lowest energy configuration, known as the vacuum state, contains fluctuations constrained by the uncertainty principle. In flat spacetime, this vacuum appears stable and featureless to inertial observers. In curved spacetime, the definition of a vacuum becomes observer-dependent. What appears empty to one observer may appear populated to another. This ambiguity becomes extreme near an event horizon. The horizon divides spacetime into regions with distinct causal structures. Observers hovering far from the black hole define particle states using a time coordinate that differs from the time experienced by observers falling inward. Quantum fields respond to this mismatch. Modes that appear purely vacuum-like to infalling observers acquire particle content when described by distant observers. This effect can be understood through the stretching of field modes by gravity. As spacetime curves more sharply near the horizon, wavelengths of quantum fluctuations experience extreme redshifting. Modes that originate close to the horizon propagate outward, their frequencies altered by the gravitational field. The separation of modes into positive and negative frequencies differs between observers at infinity and those near the horizon. From this mismatch emerges particle production. Near the horizon, quantum fluctuations constantly generate correlated excitations. These excitations can be described heuristically as pairs of field modes linked by quantum correlations. One member of each correlated pair propagates outward, while the other propagates inward toward the black hole interior. The horizon enforces this separation by preventing the inward propagating partner from influencing the exterior region. This process does not rely on a physical tearing of particles from the vacuum. It arises from the structure of quantum fields in curved space-time. The field modes straddle the horizon, and the global quantum state remains well defined. Observers restricted to the exterior region perceive a flux of particles emerging from the black hole, even though the full quantum state includes correlations that extend across the horizon. This insight was formalized in 1974 by Stephen Hawking, who performed a detailed calculation of quantum field behavior on a black hole background. Hawking considered a collapsing star that forms a black hole and studied how quantum fields evolve during this process. His calculation treated the space-time geometry classically while quantizing the fields propagating upon it, an approach now known as semi-classical gravity. The result transformed the understanding of black holes. Hawking showed that black holes emit radiation with a precisely thermal spectrum. The temperature of this radiation depends on the surface gravity of the black hole, which in turn depends on its mass, charge, and angular momentum. For a non-rotating, uncharged black hole, the temperature scales inversely with mass. Stellar mass black holes emit radiation at temperatures far below the cosmic microwave background, while smaller black holes emit at higher temperatures. This radiation emerges steadily, carrying energy away from the black hole. From the perspective of distant observers, the black hole loses mass over time. The evaporation process follows directly from energy conservation combined with the emitted flux. No additional assumptions are required. A classical black hole placed in a quantum universe behaves as a thermal emitter. The thermal nature of the radiation is central. A thermal spectrum depends only on a small number of macroscopic parameters. Temperature determines the distribution of emitted energies, and chemical potentials determine particle species. Thermal radiation carries no memory of the detailed processes that produced it. Photons emitted by a hot object reveal its temperature, not the microscopic configurations of its atoms. Hawking radiation shares this property. The emitted particles form a blackbody spectrum modulated only by grey body factors that account for scattering in the curved space-time surrounding the black hole. These factors adjust intensities but preserve the thermal character. The radiation depends solely on the black hole's global parameters, not on the specific states of matter that previously fell in. This feature creates a sharp contrast with ordinary quantum evolution. When a quantum system emits radiation through unitary processes, the outgoing radiation remains entangled with the internal degrees of freedom. In principle, careful measurements of the radiation could reconstruct information about the initial state. Thermal radiation lacks such structure. It represents a mixed state, characterized by probabilities rather than coherent phase relationships. In Hawking's calculation, the radiation observed at infinity appears exactly thermal. The outgoing modes remain entangled with partner modes that propagate into the black hole interior. External observers, who trace over inaccessible interior degrees of freedom, describe the radiation using a thermal density matrix. From their perspective, the radiation carries entropy, but no recoverable information about the initial quantum state of the collapsing matter. This description fits naturally within semi-classical gravity. The black hole interior provides a sink for correlations. The global quantum state remains pure, yet external observers encounter a mixed state because part of the system lies beyond causal reach. In this picture, information resides within the interior, encoded in correlations between interior and exterior modes. As evaporation proceeds, however, the picture acquires new significance. The black hole shrinks as radiation carries energy away. If evaporation continues until the black hole disappears, the interior region ceases to exist as a distinct space-time domain. The partner modes that once stored correlations no longer have a place within the classical description. At this stage, the thermal character of Hawking radiation becomes more than a feature. It becomes a challenge. Thermal emission suggests that the radiation lacks the detailed correlations required to encode the full information content of the initial state. If the black hole evaporates completely, the final state of the universe appears to consist of thermal radiation alone. Quantum mechanics demands a unitary mapping between initial and final states. A pure initial state evolving into a mixed final state contradicts this demand. Hawking's result therefore implies a breakdown of quantum determinism when combined with complete evaporation. This implication did not arise from approximation error or speculative reasoning. It followed directly from applying established quantum field theory to curved spacetime. The apparent information-free nature of Hawking radiation lies at the heart of the paradox. Thermal spectra reflect maximal entropy for a given energy. They represent states where microscopic distinctions have been averaged out. In statistical mechanics, thermal states arise when systems equilibrate internally. In Hawking radiation, thermal emission arises from tracing over inaccessible degrees of freedom rather than internal equilibration. This distinction matters. If the radiation truly lacks correlations with earlier states, then information about infalling matter fails to appear in the exterior universe. If those correlations remain hidden until the end, their disappearance raises a fundamental inconsistency. The thermal spectrum appears indifferent to the history of the black hole. The calculation itself remains robust. Over decades, Hawking radiation has been derived using multiple independent methods, including path integrals, Bogoliubov transformations, and tunneling pictures. Each approach confirms the thermal character of the emission. Modifications adjust details, but preserve the central result. This robustness elevates the paradox. The challenge does not lie in the existence of Hawking radiation. It lies in understanding how its thermal nature coexists with quantum information conservation. The radiation carries entropy. The black hole loses mass. The interior shrinks. The bookkeeping of information becomes unavoidable. At this point, classical thinking no longer suffices. Black holes behave as thermodynamic objects that radiate. Quantum fields respond to curved spacetime in ways that generate entropy. The horizon emerges as an active participant in quantum processes rather than a passive boundary. Hawking radiation therefore represents more than an exotic prediction. It marks the moment when gravity, quantum theory, and thermodynamics intersect directly. The smooth horizon of classical geometry becomes a source of particles. The simplicity of black holes becomes statistical rather than absolute. The stage is set for a deeper confrontation between the principles of quantum mechanics and the structure of space-time. From here, the information paradox sharpens. The radiation that escapes appears thermal and indifferent. The laws of quantum theory demand preservation of distinctions. Reconciling these facts drives the next phase of the story, where information loss becomes a precisely formulated problem rather than an abstract concern. A massive star collapses under gravity, space-time folds inward, and an event horizon forms. From the outside, the process appears violent at first and then settles into stillness. Matter crosses the horizon, radiation fades, and the black hole relaxes into a stationary state defined only by mass, angular momentum, and charge. This is the beginning of the sequence that defines the information loss paradox. The second stage unfolds slowly. Quantum fields surrounding the black hole generate Hawking radiation. Particles stream outward, carrying energy away. The black hole's mass decreases gradually, its horizon shrinking over immense timescales. For stellar mass black holes, this process extends far beyond the current age of the universe. For smaller black holes, the timescale shortens, yet the structure of the process remains the same. Radiation continues, energy leaks away, and the black hole evolves. The final stage follows directly. If Hawking radiation persists, the black hole approaches complete evaporation. The horizon contracts toward zero size. The interior space-time region disappears from the classical description. What remains is a universe containing radiation propagating outward, with no remaining region that corresponds to the black hole itself. This sequence, formation, evaporation, disappearance, appears straightforward within semi-classical gravity. Each step follows from combining general relativity with quantum field theory. The paradox emerges when this sequence is examined through the lens of quantum mechanics. Consider the quantum state of the system at the beginning. A collapsing star, together with its surrounding fields, can be described by a pure quantum state. A pure state encodes maximal information. It represents a complete specification of the system's quantum configuration, including all phase relationships between components of the wave function. As collapse proceeds, the black hole forms and Hawking radiation begins. Each emitted quantum remains entangled with degrees of freedom associated with the black hole interior. From the perspective of an external observer, the radiation appears thermal because the interior degrees of freedom are inaccessible. The external observer describes the radiation using a mixed state, characterized by probabilities rather than coherent amplitudes. At intermediate times, this description remains compatible with quantum mechanics. The full system, including both the radiation and the black hole interior, still resides in a pure global state. The appearance of a mixed state arises from tracing over degrees of freedom that lie beyond observational reach. Information resides in correlations rather than in accessible observables. The problem arises at the end of evaporation. When the black hole disappears, the interior degrees of freedom that carried correlations no longer exist within the classical spacetime description. The final state of the universe consists only of Hawking radiation propagating outward. That radiation, according to the original calculation, retains its thermal character. A thermal state is a mixed state. It contains entropy. It lacks the phase correlations that characterize a pure state. If the final state is mixed while the initial state was pure, the mapping between initial and final states becomes many to one. Distinct initial configurations collapse onto the same final thermal outcome. This outcome directly violates unitarity. Quantum mechanics requires that time evolution preserve the purity of states for closed systems. A pure state evolving into a mixed state under deterministic dynamics contradicts this requirement. The evolution fails to remain invertible. Information about the initial configuration becomes unrecoverable, even in principle. This violation strikes at the mathematical foundation of quantum theory. Unitarity ensures probability conservation, consistency of interference effects, and the reliability of experimental predictions. Without it, the framework loses coherence. Measurements performed at late times fail to encode sufficient information to reconstruct earlier states, even in principle. The issue extends beyond technical detail. Quantum mechanics relies on linearity and unitarity to maintain causal structure and logical consistency. If evolution allows pure states to degrade into mixed states without an environment to trace over, the distinction between dynamics and measurement blurs. The theory loses its ability to sharply define physical processes. One could attempt to reinterpret the evaporation process as involving an environment beyond description. Yet this approach shifts rather than resolves the problem. In ordinary quantum systems, mixed states arise because subsystems interact with external degrees of freedom. In black hole evaporation, the system under consideration includes all known degrees of freedom. There is no larger environment available to absorb information. This is what elevates the information loss paradox from a technical puzzle to a foundational inconsistency. It presents a conflict between two principles that define modern physics. General relativity predicts horizons in spacetime regions that become causally disconnected. Quantum mechanics demands that information encoded in physical states persists through time. The paradox cannot be dismissed as an artifact of approximation without careful justification. Hawking radiation emerges from well-tested quantum field theory applied to curved space-time. Event horizons arise naturally from Einstein's equations. Both frameworks succeed independently across enormous domains of experiment and observation. Their combination leads directly to the paradox, nor does the paradox depend on extreme speculation about singularities. It arises from low-energy physics near the horizon, far from Planck-scale curvature. The wavelengths involved in Hawking radiation stretch to macroscopic scales by the time they reach distant observers. The calculation relies on physics that remains under theoretical control. The framing of the paradox therefore becomes precise. A black hole forms from matter in a pure quantum state. The black hole evaporates through thermal radiation. The final state appears mixed. Quantum mechanics requires unitary evolution. These statements cannot all be true simultaneously. One of them must give way or be reinterpreted. Either black holes do not evaporate completely, or Hawking radiation deviates from perfect thermality, or quantum mechanics requires modification, or spacetime geometry behaves differently from classical expectations. Each possibility carries profound implications. This clarity marks a turning point. The information loss paradox no longer rests on intuition or analogy. It becomes a sharply defined contradiction between mathematical structures. It challenges the completeness of semi-classical gravity and demands a deeper theory that unifies space-time geometry with quantum information. From this point forward, the discussion shifts. Proposed resolutions must account for how information escapes, where it resides, or how the principles themselves adapt. The paradox stands as a diagnostic tool, exposing the limits of existing theories and pointing toward a deeper understanding of quantum gravity. The story continues from here, driven by attempts to preserve unitarity, reinterpret horizons, and uncover the microscopic structure underlying black hole thermodynamics. As the information loss paradox took shape, the first responses emerged during the late 1970s and 1980s, a period when quantum gravity remained largely unexplored territory. Physicists confronted a choice that felt unprecedented. Either one of the most successful theories ever constructed required modification, or black holes possessed properties that classical intuition had concealed. The earliest proposed resolutions reflected the uncertainty of that moment, exploring possibilities that ranged from radical to conservative, each attempting to restore internal consistency. One response accepted the paradox at face value and treated information destruction as a genuine physical process. In this view, black hole evaporation marked a fundamental departure from ordinary quantum evolution. Pure states could evolve into mixed states. Unitarity would serve as an approximation rather than an absolute law. Gravity, acting through horizons and singularities, would introduce irreducible randomness into the universe. This proposal possessed a certain directness. Hawking himself initially supported this interpretation, arguing that space-time topology change associated with black holes might invalidate the assumptions underlying unitary evolution. The loss of information would then reflect a new physical principle rather than a failure of calculation. Quantum mechanics would require generalization in the presence of strong gravitational fields. Yet this approach quickly encountered structural difficulties. Quantum mechanics relies on unitarity to preserve probability and ensure consistency across measurements. Abandoning unitarity introduces ambiguities into time evolution. Predictive power weakens. Correlations between experiments performed at different times become ill-defined. The clean separation between dynamics and measurement erodes. More subtly, information destruction threatens locality and causality. If pure states can degrade into mixed states through gravitational processes, then distant observers lose the ability to infer earlier conditions even in principle. The logical structure that supports quantum field theory and statistical mechanics becomes unstable. Rather than resolving the paradox, this approach spreads inconsistency throughout the framework. A second class of proposals aim to preserve unitarity by storing information in long-lived remnants. In this picture, black hole evaporation halts at a small mass scale, leaving behind a stable or metastable object with Planck scale size. These remnants would carry the information associated with everything that fell into the original black hole. Evaporation would reduce the black hole's mass, yet a core would remain, acting as a container for information. At first glance, remnants offer an economical solution. Information remains localized within a physical object. Hawking radiation remains thermal throughout evaporation. Unitarity survives because the final state includes both radiation and the remnant. No modification to quantum mechanics appears necessary. The difficulty lies in accounting for the information capacity of such objects. A black hole formed from an arbitrarily large amount of matter would need to store an arbitrarily large amount of information. A remnant with fixed microscopic size would then require an unbounded number of internal states. This leads to pathological consequences. Objects with infinite internal degeneracy behave unpredictably in quantum field theory. They would contribute divergent effects to vacuum processes. Pair production of remnants would dominate interactions, destabilizing ordinary spacetime. The absence of observational evidence for such effects deepened skepticism toward the remnant hypothesis. Another proposal invoked baby universes. In this scenario, information carried into a black hole would exit spacetime entirely, branching into a disconnected region. From the perspective of the original universe, information would appear lost. From a broader multiverse perspective, information would persist, conserved across a larger structure. This approach reframed the paradox by expanding the system under consideration. Unitarity would apply to the combined system of parent universe plus baby universes. The apparent loss of information would reflect incomplete bookkeeping rather than fundamental destruction. Despite its conceptual appeal, this idea encountered obstacles. Baby universes lack direct observational support. Their inclusion complicates quantum field theory by introducing new sectors that influence low-energy physics through subtle effects. Coupling constants could fluctuate unpredictably. Predictive power again weakens. Moreover, the information paradox concerns what observers within a given universe can recover. Shifting information to inaccessible regions does not resolve the operational problem. For observers restricted to a single spacetime, information remains effectively lost. The paradox reappears in practical terms even if global conservation is preserved. Some approaches explored explicitly non-unitary models of quantum gravity. These frameworks attempted to modify the Schrödinger equation or introduce stochastic elements into time evolution. Gravity would act as a decohering influence, converting pure states into mixed states through intrinsic dynamics rather than environmental interaction. These models sought mathematical consistency, yet they struggled to reproduce the empirical success of ordinary quantum mechanics. Experiments across atomic, nuclear, and particle physics show no deviations from unitary evolution. Any modification strong enough to resolve black hole evaporation would need to remain suppressed across all accessible energy scales while emerging only in extreme gravitational regimes. Achieving this balance proved difficult. Non-unitary effects tend to leak into ordinary processes unless carefully constrained. Such leakage would produce observable violations of energy conservation or probability normalization. The absence of such observations placed tight bounds on these proposals. Across these early efforts, a common pattern emerged. Each proposal addressed one aspect of the paradox, while introducing new difficulties elsewhere. Information destruction undermined quantum consistency. Remnants destabilized quantum field theory. Baby universes weakened predictability. Non-unitary gravity conflicted with experimental evidence. Rather than dissolving the paradox, these ideas sharpened it. They clarified what a successful resolution must accomplish. Any viable theory would need to preserve unitarity without introducing unobservable infinities or destabilizing known physics. It would need to respect causality, maintain predictive power, and align with established quantum behavior at accessible scales. By the early 1990s, it became clear that the paradox pointed toward a deeper restructuring rather than a local fix. Black holes demanded a microscopic description compatible with quantum information theory. Horizons required internal structure or new principles governing their behavior. Gravity and quantum mechanics could no longer be treated as loosely connected frameworks. These early proposals played a crucial role by mapping the landscape of possibilities. They demonstrated which paths led to contradiction and which constraints remained non-negotiable. In doing so, they prepared the ground for a more refined approach, one that would preserve quantum determinism while reinterpreting the nature of space-time itself. The search for such an approach would soon shift toward ideas that treated horizons not as passive boundaries, but as active carriers of information, reshaping how black holes and quantum mechanics could coexist. Black hole complementarity emerged as an attempt to preserve quantum mechanics without forcing dramatic changes to known physics. It did not introduce new particles or alter the equations of motion. Instead, it re-examined how physical descriptions apply to different observers in the presence of horizons. The proposal rests on a single guiding idea: a complete physical description does not need to be globally accessible to every observer at once. In ordinary situations, different observers can describe the same physical process using different coordinate systems or reference frames, yet agree on all measurable outcomes. Black hole complementarity extends this logic to its extreme. It asserts that observers outside a black hole and observers falling into it each possess valid, self-consistent descriptions of reality, even though those descriptions cannot be combined into a single global picture. For an external observer hovering far from the black hole, the event horizon behaves as a physical surface. Infalling matter approaches the horizon, slows due to gravitational time dilation, and appears increasingly redshifted. Information carried by that matter never seems to cross the horizon within finite external time. Instead, it becomes encoded in degrees of freedom associated with the horizon itself. From this viewpoint, the black hole acts as a hot quantum object with microscopic structure spread across its surface. For an infalling observer, the experience differs completely. Crossing the horizon involves no violent event. Spacetime remains locally smooth. Classical general relativity predicts that the horizon carries no special local signature. The observer continues inward, carrying their information with them, unaware of any horizon-based encoding described by external observers. Complementarity asserts that both descriptions remain correct within their respective domains. The key restriction lies in operational access. No observer can simultaneously verify both descriptions. External observers never witness matter crossing the horizon. Infalling observers never communicate their observations back out. The causal structure of spacetime enforces this separation. This separation resolves the most immediate contradiction. If information appears to be stored on the horizon for external observers and carried smoothly inward for infalling observers, there seems to be duplication. Quantum mechanics prohibits copying unknown quantum states. Complementarity avoids this violation by denying the possibility of a single observer detecting both copies. The apparent duplication lacks physical consequence. This reasoning addresses the cloning paradox directly. In quantum information theory, cloning becomes problematic only when an observer can access both the original and the copy. In the black hole context, no observer ever encounters both the horizon-encoded information and the infalling information. The causal structure blocks any experiment capable of detecting duplication. Complementarity therefore maintains consistency with quantum principles. The horizon occupies a dual role in this framework. It functions as an effective information-bearing surface for distant observers, while remaining an unremarkable geometric feature for infalling observers. The horizon's reality becomes observer-dependent rather than absolute. This departure from classical intuition represents a significant conceptual shift. From the external viewpoint, the horizon acquires thermodynamic properties. It absorbs, scrambles, and later re-emits information through Hawking radiation. Information spreads across the horizon degrees of freedom and emerges only after long delays, consistent with unitary evolution. From the infalling viewpoint, no such process is experienced locally. Information continues inward without disruption. The strength of complementarity lies in its economy. It preserves quantum mechanics, respects general relativity locally, and aligns with known semi-classical results. It avoids invoking exotic remnants or modifying fundamental equations. It treats the paradox as a problem of description rather than dynamics. Complementarity also fits naturally with the idea that horizons limit what can be operationally measured. Physics concerns predictions about experiments. If no experiment can reveal a contradiction, then the theory remains internally consistent. Complementarity leans heavily on this operational philosophy. Despite its appeal, the proposal carries internal tensions. It requires that the horizon behave like a quantum system with an enormous number of degrees of freedom, yet classical general relativity assigns no such structure. The theory offers no microscopic model explaining how information becomes encoded on the horizon or how it later emerges through radiation. Another tension arises from the timing of information recovery. For information to emerge in Hawking radiation while remaining inaccessible to infalling observers, the horizon must process and scramble information rapidly. This assumption introduces dynamical requirements that extend beyond the original semi-classical framework. More sharply, complementarity faces challenges when entanglement enters the discussion. Hawking radiation emitted early becomes entangled with radiation emitted later. At the same time, outgoing radiation remains entangled with modes just inside the horizon. Maintaining all these entanglement relationships simultaneously strains the consistency of the picture. These issues would later crystallize into deeper conflicts. Complementarity also relies heavily on the assumption that no observer can compare notes across the horizon. Thought experiments that attempt to probe both descriptions indirectly expose subtle inconsistencies. While no real experiment can violate causal structure, carefully constructed theoretical scenarios begin to test the limits of the proposal. Even so, black hole complementarity marked a turning point. It reframed the paradox in terms of observer-dependent physics and information flow rather than outright loss. It suggested that spacetime itself might encode information in ways that defy classical global descriptions. The proposal did not settle the paradox, yet it clarified what a resolution might look like. Information could remain preserved without being globally accessible. Horizons could carry operational meaning without possessing invariant local structure. Quantum mechanics could survive intact, provided classical intuitions about spacetime gave way. The next developments would push these ideas further, forcing complementarity to confront its own assumptions and exposing where its internal balance begins to strain under the full weight of quantum entanglement. When the information paradox is formulated in words, it sounds like a clash of intuitions. Black holes swallow detail, quantum mechanics preserves it. When it is formulated in equations, it becomes something sharper, a prediction about how entanglement entropy must evolve over time. This quantitative framing turns the paradox into a falsifiable consistency test. It asks a specific question about the radiation emitted by an evaporating black hole. How much quantum information does that radiation carry as evaporation proceeds? The relevant quantity is entanglement entropy. In quantum theory, a composite system can occupy a pure global state while its subsystems appear mixed. The measure of this apparent mixedness is the von Neumann entropy of the subsystem's density matrix. For a bipartite system split into parts A and B, the entanglement entropy of A equals the entanglement entropy of B when the total state is pure. Entanglement entropy therefore tracks how strongly two subsystems are correlated at the quantum level. In black hole evaporation, the natural split is between the Hawking radiation that has escaped and the degrees of freedom remaining in the black hole. Early in the evaporation process, only a small amount of radiation has escaped. That radiation appears thermal. In Hawking's semi-classical description, each outgoing quantum is entangled with a partner mode that remains inside the horizon. As a result, the radiation subsystem appears highly mixed. Its entanglement entropy increases as more quanta are emitted. This growth has a simple intuitive interpretation. Each emitted quantum carries entropy because it is entangled with something the external observer cannot access. If the black hole is treated as the inaccessible subsystem, then every emission event increases the entanglement between radiation and black hole. The radiation becomes more mixed. Its entanglement entropy rises. If evaporation ends with a final state consisting solely of thermal radiation, then the entanglement entropy of the radiation remains large. A mixed thermal state has substantial entropy, yet the initial state, before collapse, can be taken as pure. Unitary evolution from a pure initial state to a final state containing only radiation requires that the radiation be pure as a whole at the end. A pure final radiation state has von Neumann entropy equal to 0. This is the quantitative version of the paradox. To understand what unitary evaporation predicts, one can ask how entanglement entropy should behave if information is preserved. The black hole begins with a large thermodynamic entropy proportional to its horizon area. If evaporation proceeds unitarily, the total state remains pure at all times. As radiation escapes, the information that once resided in the black hole, degrees of freedom, must transfer into correlations within the outgoing radiation. This transfer implies a specific pattern. Early radiation can look thermal and carry little recoverable information. Later, radiation must deviate from perfect thermality by carrying correlations that purify the earlier radiation. At the end of evaporation, the complete set of emitted quanta must form a pure state. In entanglement entropy terms, this means the entropy of the radiation must first rise and later fall back to 0. This expected behavior is captured by the Page curve, named after Don Page, who analyzed generic properties of entanglement in large quantum systems. Consider a system initially in a pure state, divided into two subsystems. As one subsystem grows by acquiring more degrees of freedom, its entanglement entropy typically increases until the two subsystems have comparable size. After that, as the first subsystem becomes larger than the second, its entropy decreases because the smaller subsystem cannot support enough entanglement to keep the larger one maximally mixed. Applied to black holes, the Page curve predicts that the entanglement entropy of the radiation increases early on, reaches a maximum around the time when the black hole has lost about half of its entropy, and then decreases as more radiation emerges, carrying correlations that purify the earlier output. The moment of maximum entanglement is known as the Page time. It marks the turnover point when the radiation stops becoming more mixed and begins becoming more pure as a whole. The Page time scales with the evaporation process. For a non-rotating black hole, it occurs well before the final burst of evaporation, roughly when the black hole has radiated away about half of its initial entropy. The precise timing depends on grey body factors and the species of emitted particles, yet the conceptual point remains. If evaporation is unitary, the radiation cannot remain thermal throughout. It must begin to carry structure. This is where Hawking's original calculation fails the test. In the semi-classical treatment, each outgoing Hawking quantum remains entangled with an interior partner. This pairing repeats at every emission step. The entanglement entropy of the radiation therefore continues to rise monotonically throughout evaporation. The radiation remains mixed because it continues to be entangled with interior degrees of freedom. In Hawking's framework, there is no mechanism for the entanglement to turn over. The radiation never begins to purify itself. Even near the end, the outgoing quanta appear thermal. The interior partners continue to carry the correlations, yet the interior region shrinks toward disappearance. The entanglement entropy curve predicted by Hawking resembles a steadily increasing function rather than the rise and fall shape required by unitarity. This mismatch converts the paradox into a clean, quantitative inconsistency. The Page curve represents the expected behavior of entanglement entropy in unitary evaporation. Hawking's semi-classical calculation produces a different curve. Both cannot describe the same physical process. The significance of this quantitative restatement lies in its precision. It separates vague claims about loss from a measurable pattern of correlations. If one had access to all Hawking radiation emitted over the lifetime of a black hole, one could in principle test whether the radiation forms a pure state. Purity implies the presence of subtle correlations between early and late radiation. Thermal emission without correlations implies mixedness. The Page curve therefore becomes a diagnostic for the underlying theory. Any proposed resolution must explain how the entanglement entropy of the radiation turns over. It must identify the mechanism by which correlations migrate from the black hole into the radiation. It must show how the global state remains pure, while local observations can still approximate thermality. In this framing, the paradox becomes a statement about entanglement bookkeeping. Early radiation looks thermal because it is entangled with something. Late radiation must reduce that entanglement by sharing correlations with earlier radiation instead. The moment this transition occurs defines the Page time. A theory that preserves unitarity must reproduce the Page curve. A theory that predicts monotonic entropy growth implies information loss. With this quantitative lens, the problem sharpens further. Entanglement relationships cannot be assigned arbitrarily. Quantum theory imposes strict constraints through monogamy of entanglement. A given quantum subsystem cannot remain maximally entangled with two independent partners simultaneously. When this constraint is applied to the near-horizon pairs of Hawking's picture and the purification required by the Page curve, a deeper contradiction emerges. That contradiction will drive the next stage of the story. As the Page curve sharpened the information paradox into a quantitative problem, it exposed a deeper tension embedded within the structure of quantum entanglement itself. This tension centers on a fundamental rule: entanglement monogamy. In quantum theory, a system that is maximally entangled with one partner cannot simultaneously be maximally entangled with another independent partner. Entanglement distributes correlations in a constrained way. These constraints carry decisive consequences near a black hole horizon. In Hawking's original picture, each outgoing quantum of radiation is entangled with a partner mode just inside the event horizon. This entanglement underwrites the smoothness of spacetime at the horizon. For an infalling observer, the near-horizon region resembles empty space. Quantum fields occupy a vacuum state that extends smoothly across the horizon. This smoothness relies on strong entanglement between interior and exterior modes at short distances. At the same time, the Page curve demands that late-time radiation purify the early radiation if evaporation proceeds unitarily. After the Page time, newly emitted quanta must carry correlations that reduce the entropy of the radiation as a whole. This requires late radiation to be entangled with early radiation rather than with interior degrees of freedom. Here, the conflict becomes unavoidable. A single outgoing Hawking quantum cannot remain strongly entangled with both the interior mode that ensures horizon smoothness and the early radiation that ensures unitarity. Entanglement monogamy forbids this arrangement. One of these entanglement links must weaken or break. This observation formed the core of the argument presented in 2012 by Ahmed Al-Mhairi, Donald Marolf, Joseph Polchinski, and James Sully, now known as the AMPS argument. Their analysis reframed the information paradox as a logical trilemma involving three widely accepted principles: unitary evolution of quantum states, smooth horizons consistent with the equivalence principle, and the validity of semi-classical quantum field theory outside the horizon. The AMPS reasoning proceeds step by step. Assume that black hole evaporation is unitary, so that the final radiation state is pure. After the Page time, each newly emitted quantum must be entangled with the earlier radiation to reduce its entropy. Next, assume that semi-classical quantum field theory accurately describes physics just outside the horizon. This assumption underpins Hawking's calculation and the standard description of near-horizon modes. Finally, assume the equivalence principle holds so that infalling observers experience nothing unusual at the horizon. Under these assumptions, outgoing Hawking quanta near the horizon must remain entangled with interior partner modes to preserve the local vacuum structure. Yet unitarity requires those same quanta to be entangled with early radiation. Entanglement monogamy forbids both simultaneously. The three assumptions cannot all remain true. The AMPS conclusion follows directly. At least one of these principles must fail. Either black hole evaporation violates unitarity, or semi-classical physics fails outside the horizon, or the equivalence principle breaks down at the horizon itself. The most dramatic option involves the horizon. If the outgoing modes fail to be entangled with interior partners, then the local vacuum structure breaks down. The horizon ceases to be smooth. Instead of empty space, an infalling observer encounters high-energy excitations localized at the horizon. This hypothetical structure became known as a firewall. A firewall replaces the gentle crossing predicted by general relativity with an abrupt and violent transition. The equivalence principle states that freely falling observers experience local physics indistinguishable from that of flat spacetime. A firewall violates this principle directly. It introduces a preferred location in spacetime where classical intuition fails at macroscopic scales. This possibility unsettled the theoretical community because it targeted one of the most deeply trusted principles in gravitational physics. The equivalence principle underlies general relativity. It has been tested experimentally with extraordinary precision, suggesting its failure at horizons implied that black holes mark a fundamental exception to spacetime smoothness. Alternative responses appeared equally troubling. Abandoning unitarity would undermine quantum mechanics at its foundation. Modifying semi-classical physics outside the horizon would require new, non-local effects extending into regions where gravity remains weak. Each option demanded a radical shift in understanding. The shock arose not only from the conclusion, but from the argument's economy. The AMPS paradox did not rely on speculative quantum gravity effects or Planck-scale physics. It used entanglement, a well-understood quantum concept, applied to the near-horizon region where curvature remains modest. The contradiction emerged in a regime where existing theories should remain reliable. The firewall argument also strained black hole complementarity. Complementarity relied on the idea that no observer could access both copies of information. AMPS showed that the conflict emerges without any observer performing forbidden measurements. The inconsistency resides in the structure of entanglement itself, independent of operational access. This development forced a reassessment of earlier assumptions. Horizons could no longer be treated as passive boundaries whose properties differed only by observer perspective. Entanglement relationships demanded a more detailed accounting of how information distributes across spacetime. The firewall problem therefore marked a turning point. It sharpened the paradox beyond philosophical debate and exposed a precise incompatibility between cherished principles. The smoothness of spacetime, the unitarity of quantum mechanics, and the semi-classical description of fields could not coexist unchanged. Rather than offering a solution, the firewall argument raised the stakes. It showed that resolving the information paradox required a fundamental rethinking of how spacetime, entanglement, and information relate to one another. The horizon could no longer remain a simple geometric surface. It had to participate actively in quantum information dynamics or be replaced by something even more radical. The theoretical community reacted with intense scrutiny because the argument left little room for compromise. Any resolution would need to explain how entanglement reorganizes itself near horizons without sacrificing consistency elsewhere. This demand would drive the next generation of ideas, shifting attention toward holography, quantum geometry, and the possibility that spacetime itself emerges from patterns of entanglement. The firewall problem forced a reconsideration of where information resides in a gravitational system. If spacetime smoothness, quantum unitarity, and semi-classical physics could not coexist unchanged, then at least one of the underlying assumptions about locality and geometry required revision. The idea that emerged most powerfully from this reassessment was holography, the proposal that gravity encodes information in a fundamentally different way than ordinary quantum field theories. The holographic principle begins with a simple but radical observation. In conventional physics, the amount of information stored in a region of space scales with its volume. A gas filling a box carries entropy proportional to the number of particles inside, which grows with volume. Black holes defy this intuition. Their entropy scales with the area of the event horizon, not with the volume enclosed. This scaling suggests that the true degrees of freedom associated with gravity do not reside throughout space, but instead live on lower dimensional boundaries. The principle generalizes this observation. It proposes that the complete physical description of a region of space-time with gravity can be encoded on a boundary surface surrounding that region, using fewer dimensions. The bulk space-time, with its apparent depth and volume, becomes a derived concept rather than a fundamental one. The boundary description contains all the information needed to reconstruct bulk physics. This idea resolves several tensions at once. If information associated with matter falling into a black hole is encoded on the horizon or on a distant boundary, then it never disappears from the fundamental description. The loss of access experienced by bulk observers reflects limitations of locality rather than destruction of information. The paradox shifts from a question of loss to one of encoding. The most concrete realization of holography emerged through the ADS-CHOC-CFT correspondence, formulated by Juan Maldacena in 1997. This correspondence proposes an exact equivalence between two radically different theories. On one side lies a theory of gravity defined in a higher dimensional space-time with negative curvature. On the other lies a quantum field theory defined on the lower dimensional boundary of that space-time without gravity. In this duality, every bulk gravitational process corresponds precisely to a process in the boundary quantum field theory. Black holes in the bulk correspond to thermal states on the boundary. Bulk fields correspond to boundary operators. Time evolution in the bulk corresponds to unitary evolution on the boundary. The correspondence is exact, not approximate. The significance for the information paradox becomes immediate. The boundary theory obeys ordinary quantum mechanics and evolves unitarily by construction. Information cannot be lost in the boundary description. Since the bulk gravitational theory is equivalent to the boundary theory, information cannot be lost in the bulk either. The paradox dissolves at the level of the full, non-perturbative description. This does not imply that information flows outward through the bulk in a classical sense. Instead, information remains encoded non-locally across the boundary degrees of freedom. Bulk locality emerges only approximately as a low-energy, coarse-grained description. At the fundamental level, information is distributed in patterns that span large regions of the boundary. This non-local encoding changes how horizons are interpreted. A black hole horizon no longer acts as a one-way membrane that hides information permanently. Instead, it reflects a reorganization of boundary degrees of freedom into a highly entangled state. The apparent interior of the black hole corresponds to particular entanglement structures within the boundary theory. In this framework, gravity itself appears emergent. The geometry of spacetime arises from collective behavior of underlying quantum degrees of freedom. Distances, causal structure, and curvature reflect patterns of entanglement rather than primitive ingredients. When entanglement changes, geometry responds. This perspective offers a natural explanation for the entropy-area relationship. The number of boundary degrees of freedom associated with a region scales with its surface area. Entropy counts configurations of these boundary variables. Bulk volume plays no fundamental role in information storage. Information preservation follows directly. Since the boundary theory evolves unitarily, information remains present at all times. Black hole evaporation corresponds to a unitary process in the boundary description. The apparent thermality of Hawking radiation reflects coarse graining over boundary degrees of freedom rather than fundamental loss. From the bulk viewpoint, this preservation appears subtle. Information emerges slowly and in highly scrambled form. Local observers detect radiation that looks thermal. Recovering information requires access to delicate correlations spread across the radiation and encoded non-locally. The difficulty of reconstruction reflects complexity, not destruction. Holography also reframes earlier puzzles. Complementarity becomes a natural feature of dual descriptions. Interior and exterior viewpoints correspond to different ways of organizing the same boundary information. The firewall tension weakens because the smoothness of the horizon and the preservation of information arise from a deeper, non-local structure that transcends classical space-time intuition. This approach does not trivialize the paradox. It explains why semi-classical reasoning breaks down in subtle ways near horizons. It shows that locality, a guiding principle of ordinary field theory, becomes approximate in gravitational systems. Information remains conserved, yet it ceases to be localized in any simple geometric region. Holography therefore represents a decisive conceptual shift. Black holes no longer threaten quantum mechanics. Instead, they expose the limits of classical space-time descriptions. Information survives, encoded across boundaries rather than volumes, preserved by non-local correlations rather than classical trajectories. The implication reaches beyond black holes. If space-time geometry emerges from quantum information, then gravity itself becomes a collective phenomenon. Understanding horizons requires understanding entanglement. The information paradox transforms into a guide pointing toward a deeper theory in which space, time, and gravity arise from quantum structure rather than standing apart from it. This realization sets the stage for the final pieces of the puzzle, where entanglement, geometry, and quantum extremal surfaces combine to show explicitly how information reappears in black hole evaporation without violating any fundamental principle. Once information preservation is accepted as a requirement, the question shifts from whether black holes return information to how they process it. The emerging picture does not resemble ordinary storage or delayed release. Instead, black holes behave as extreme information processors, systems that rapidly mix quantum data into highly complex correlations. This behavior is captured by the idea of black holes as fast scramblers. Scrambling refers to the process by which localized information becomes distributed across all degrees of freedom of a system through unitary evolution. In a scrambled state, information remains present but is no longer accessible through local measurements. Recovering it requires probing global correlations involving many degrees of freedom at once. Scrambling does not destroy information, it hides it in complexity. In quantum many-body systems, scrambling is associated with quantum chaos. Small perturbations spread rapidly, influencing an ever-growing fraction of the system. Near a black hole horizon, gravity amplifies this effect. The strong gravitational field stretches and redshifts modes, enhancing sensitivity to initial conditions. Quantum information that falls toward the horizon becomes rapidly entangled with horizon degrees of freedom. This behavior contrasts with ordinary thermal systems. In a gas or solid, scrambling occurs through local interactions that propagate information at finite speeds. The timescale for complete scrambling grows with system size. Black holes operate differently. Their horizon geometry enables interactions that mix information across the entire surface with remarkable efficiency. The concept of black holes as fast scramblers was formalized by Leonard Susskind and Yasuhiro Sekino, who argued that black holes scramble information at the fastest rate allowed by quantum mechanics. This rate scales logarithmically with the number of degrees of freedom rather than linearly. For a black hole, the relevant number of degrees of freedom scales with its entropy, which is proportional to horizon area. The scrambling time for a black hole therefore scales as the logarithm of its entropy multiplied by a characteristic timescale set by the inverse temperature. For astrophysical black holes, this scrambling time remains extremely short compared to the total evaporation time. Even for stellar mass black holes, scrambling occurs in milliseconds, while evaporation takes far longer than the current age of the universe. This separation of timescales matters. Information that falls into a black hole becomes rapidly distributed across horizon degrees of freedom long before significant evaporation occurs. The black hole forgets the localized form of the information quickly, yet it retains the information globally in a highly entangled state. Evaporation unfolds on a much longer timescale. Hawking radiation carries energy away slowly. If information is encoded in subtle correlations among horizon degrees of freedom, then its release through radiation requires careful accounting of these correlations. Early radiation carries little recoverable information because the scrambling process has not yet reorganized correlations in a way that allows purification. This intuition was sharpened by a thought experiment introduced by Patrick Hayden and John Preskill. They considered a black hole that has already passed the page time, meaning it has emitted more than half of its entropy in radiation. At this stage, the radiation already carries substantial information about the black hole's internal state. In the Hayden-Preskill scenario, an observer throws a small quantum system into such an old black hole. The question becomes how long it takes before information about that system appears in the outgoing radiation. The surprising answer follows from fast scrambling. Once the new information becomes scrambled across the horizon, it can begin to emerge almost immediately in the radiation. The delay between infall and recoverability scales with the scrambling time, not the evaporation time. After scrambling, the next emitted Hawking quanta can carry correlations that encode the newly added information. In principle, an observer who has access to the earlier radiation and performs extremely complex decoding operations could recover the infalling quantum state after a relatively short delay. This result reshapes intuition about black holes. They do not store information passively for most of their lifetime and then release it only at the end. Instead, after the page time, they behave more like mirrors that reflect information back out, though in an extraordinarily scrambled form. The difficulty lies not in the timing, but in the complexity of decoding. Information recovery therefore becomes a problem of computational complexity rather than fundamental dynamics. The correlations that encode information are spread across many degrees of freedom. Extracting them requires global measurements and operations that scale exponentially with system size. Practical recovery remains infeasible, yet the laws of quantum mechanics permit it in principle. Causality imposes strict limits on this process. No signal escapes faster than light. Information cannot be recovered before the black hole has had time to scramble it and emit correlated radiation. The Hayden-Preskill result respects these constraints. The recovery time exceeds the scrambling time and includes delays associated with signal propagation and radiation emission. The horizon plays a central role in enforcing these limits. Information crossing the horizon becomes causally disconnected from the exterior in classical terms. In the quantum description, however, information becomes encoded in correlations that straddle the horizon and later reappear through radiation. This reappearance does not involve superluminal signaling. It reflects the unfolding of unitary evolution constrained by spacetime geometry. Fast scrambling also clarifies why Hawking radiation looks thermal locally. Individual quanta appear random because they sample only a tiny fraction of the global correlations. The structure that preserves information exists at a scale that spans many emissions. Local measurements detect noise. Global measurements reveal order. This picture reconciles several earlier tensions. It explains how information can remain preserved while remaining inaccessible to ordinary observers. It shows why evaporation can appear thermal while still respecting unitarity. It preserves causality while allowing recovery in principle. Black holes therefore emerge as extreme quantum systems that operate at the edge of physical limits. They scramble information as rapidly as allowed. They release it slowly through radiation. The apparent simplicity of their external behavior masks an internal dynamical complexity governed by entanglement and chaos. Understanding black holes as fast scramblers reframes the paradox once more. Information loss gives way to information delocalization and delayed accessibility. The remaining challenge lies in making this picture precise within a gravitational framework, identifying how space-time geometry encodes and releases these correlations. That challenge leads directly toward newer tools that combine geometry, entropy, and quantum extremal surfaces. In the years when the information paradox felt sharpest, the tension came from a simple semi-classical habit: treat spacetime as classical, quantize fields on top of it, and compute what an outside observer sees. That method works extraordinarily well for many settings in curved spacetime, and it produces Hawking's thermal radiation with impressive robustness. Yet the page curve asked for something the original semi-classical bookkeeping never delivered: a late-time turnover in the fine-grained entropy of the radiation. The breakthrough of the last decade came from learning how to compute that fine-grained entropy in a gravitational setting with the same seriousness that quantum theory demands. In ordinary quantum systems, the fine-grained entropy of a subsystem is computed from its reduced density matrix. One takes the global state, traces out degrees of freedom outside the chosen subsystem, and calculates the von Neumann entropy. Gravity complicates this step because space-time itself becomes dynamical, and the very definition of inside and outside becomes subtle when the geometry can respond to the state. The modern story begins with a method that predates black holes and reaches back into the foundations of quantum field theory: the replica trick. The replica trick is a computational strategy for entanglement entropy. Instead of trying to take a logarithm of a density matrix directly, one computes a family of replicated partition functions. One considers an integer number of copies of the system sewn together along the region whose entropy one wants. From these replicated geometries, one computes a Rényi entropy, and then one analytically continues the replica number to 1 to obtain the von Neumann entropy. In non-gravitational quantum field theory, this is a standard approach. It translates an entropy problem into a path integral problem. The new ingredient arises when gravity participates in the path integral. When one performs the replica trick in a theory with dynamical geometry, one must sum over geometries consistent with the replicated boundary conditions. That sum includes saddle points that have no counterpart in the non-gravitational calculation. In particular, the replicated geometries can connect to one another through space-time wormholes that link different replicas. These replica wormholes sound exotic in name, yet in practice they are semi-classical saddle points of the gravitational path integral. They change the dominant contribution to the entropy at late times. This is where quantum extremal surfaces enter. In holographic settings, the Ryu-Takayanagi prescription taught that the entanglement entropy of a boundary region can be computed from the area of a minimal surface in the bulk anchored to that region. That original formula captured leading classical contributions. Engelhardt and Wall generalized it to include quantum corrections, replacing minimal surfaces with quantum extremal surfaces. A quantum extremal surface is a bulk surface that extremizes a generalized entropy, an area term plus the entanglement entropy of quantum fields across that surface. The area reflects the gravitational part, and the bulk entanglement reflects quantum fields living on the geometry. A remarkable feature of this generalized entropy is that it behaves like the correct fine-grained entropy in gravitational systems. It treats entropy as an object with both geometric and quantum components, and it allows the extremization procedure to select the correct surface dynamically. In practice, one computes the generalized entropy for candidate surfaces and selects the one that yields the smallest generalized entropy after extremization. The phrase smallest matters because multiple extremal surfaces can exist, and the dominant one changes as the system evolves. When this machinery is applied to evaporating black holes, It produces a conceptual reclassification of what the radiation region actually contains in the fine-grained sense. One begins by defining a radiation region in a non-gravitating bath, where Hawking quanta propagate outward and can be collected. From an ordinary quantum field theory viewpoint, the entropy of that radiation region is computed solely from the bath degrees of freedom. Gravity changes the answer because the correct saddle point for the entropy calculation can include an additional region inside the gravitational spacetime, an island. An island is a region in the gravitational bulk that must be included as part of the entanglement wedge of the radiation when computing the fine-grained entropy. Operationally, the entropy of the radiation is not computed as the entropy of the bath alone. Instead, one computes the generalized entropy of the union of the bath radiation region and a candidate island region, then extremizes over possible island locations, and finally chooses the dominant saddle. This procedure is often summarized as an island formula, yet the deeper idea is that the entropy calculation itself selects which bulk degrees of freedom belong to the radiation's entanglement wedge. Early in evaporation, the dominant saddle has no island. The radiation entropy grows in the familiar way because each emitted quantum is entangled with degrees of freedom that remain associated with the black hole. In this regime, the semi-classical intuition holds. Tracing over the black hole yields a mixed radiation state with increasing entropy. At late times, a new saddle becomes dominant. A quantum extremal surface appears near the horizon, and an island region inside the black hole becomes included in the entropy calculation for the radiation. The presence of the island changes the meaning of what has been traced out. Degrees of freedom in the island count as part of the radiation subsystem for the purposes of fine-grained entropy. That inclusion reduces the entropy because the island region contains correlations that purify the radiation. This change produces the page curve directly. The radiation entropy rises at early times, reaches a maximum around the page time, and then decreases as the island saddle dominates. The turnover is not inserted by hand. It emerges as a phase transition between two competing saddles of the gravitational replica trick. The curve matches the qualitative and quantitative behavior expected from unitarity. The page time receives a clean geometric interpretation in this framework. It is the time when the generalized entropy of the no-island saddle equals the generalized entropy of the island saddle. Before that moment, excluding the island yields the smallest entropy. After that moment, including the island yields the smallest entropy. The transition resembles other semi-classical phase transitions, where one saddle overtakes another as parameters change. The novelty is that the parameter here is time, and the object that changes discontinuously is the entanglement wedge of the radiation. This explains why semi-classical gravity needed correction without discarding the core Hawking computation. Hawking's local calculation near the horizon remains accurate for the outgoing flux and its approximate thermality. What it misses is a global, non-perturbative contribution to the fine-grained entropy that appears in the gravitational path integral. The missing piece comes from replica wormholes and the resulting quantum extremal surface saddles. These effects remain invisible in a purely local treatment because they involve correlations encoded in the global structure of the state and its gravitational saddles. One way to see the distinction is to separate coarse-grained and fine-grained entropy. The radiation can look thermal in coarse-grained observables while still carrying fine-grained correlations that purify it. Hawking's result captures the coarse-grained thermality well. The island framework addresses the fine-grained entropy accounting that unitarity constrains. In this view, the paradox emerged because a coarse-grained semi-classical intuition was being asked to deliver a fine-grained quantum answer. The island picture also reframes the role of the black hole interior. In semi-classical language, the interior partner modes of Hawking quanta appear to sit behind the horizon, entangled with the radiation outside. After the page time, The island saddle implies that a region inside the horizon is encoded in the radiation's entanglement wedge. This does not mean that classical signals travel outward from behind the horizon. It means that the quantum information describing those interior degrees of freedom is redundantly represented in the radiation in a way consistent with holography and quantum error correction. The interior becomes a recoverable description from the radiation, at least in principle, even while local causal structure remains intact. This changes the intuitive status of the horizon. The horizon continues to act as a causal boundary for classical communication, and local physics near it can remain smooth in appropriate descriptions. Yet the entanglement bookkeeping assigns part of what one would have called inside to the radiation subsystem at late times. The boundary between inside and outside becomes state-dependent in the entanglement sense, selected by the quantum extremal surface. Modern consensus has formed around the idea that these developments represent genuine progress rather than a clever accounting trick. The page curve emerges in explicit, solvable models, often in lower dimensional gravity, coupled to bath systems, where the island formula can be evaluated cleanly and compared to expectations from unitary quantum systems. The calculations show that the fine-grained entropy follows the unitary page curve once islands are included. Reviews by Almheri and others emphasize that the methodology builds on gravitational entropy techniques developed over many years and gains new power when applied to evaporating black holes. At the same time, the consensus remains careful about interpretation. The island mechanism tells a consistent story about entropy and information in a semi-classical plus non-perturbative framework, and it aligns naturally with holography. It indicates that semi-classical gravity, used naively, undercounts contributions that become crucial for fine-grained questions. It also suggests that non-local encoding of information, familiar from holography, becomes unavoidable in gravitational systems. This does not turn black hole evaporation into an easy decoding problem. Scrambling and complexity still dominate practical recoverability. The island formula guarantees that information preservation is compatible with semi-classical radiation and smooth horizons at the level of entropy accounting. It supplies the missing turnover in the page curve without requiring firewalls as a universal feature. What changes most is the posture of the paradox itself. Information loss ceases to look like a direct prediction of combining quantum fields with classical geometry. It becomes a symptom of asking for a fine-grained answer while restricting attention to a subset of saddles in the gravitational path integral. When the full semi-classical saddle structure is included, the entropy behaves as unitarity requires. In that sense, quantum extremal surfaces and islands provide more than a resolution of a curve on a plot. They supply a sharpened lesson about gravity. Geometric notions of region, boundary, and subsystem do not behave like their counterparts in ordinary quantum field theory. In gravitational settings, the correct definition of a subsystem for entanglement purposes is dynamical. It is selected by extremization of generalized entropy. The inside of a black hole can become part of the radiation's entanglement wedge, and the fine-grained entropy responds accordingly. The information paradox began as a story about disappearance. Here it becomes a story about accounting, saddles, and the surprising way quantum information reorganizes the meaning of space. Once islands and quantum extremal surfaces reframed the information problem, a deeper pattern became difficult to ignore. The mechanisms that restore unitarity do not merely hide information more cleverly. They suggest that space-time geometry itself responds to, and even arises from, quantum entanglement. In this view, gravity no longer acts as a background stage on which quantum information moves. Geometry becomes a secondary structure, shaped by correlations in an underlying quantum state. The first clues come from how entanglement behaves in many-body quantum systems. Entanglement is not an abstract bookkeeping device. It constrains how information distributes itself across subsystems and how those subsystems relate to one another. In gravitational settings, those constraints appear to organize space-time itself. Distances, connectivity, and even the existence of an interior region begin to track patterns of entanglement rather than classical coordinates. This idea gained traction through holography, where bulk geometry responds directly to boundary entanglement. In ADS CFT, the entanglement entropy of a region in the boundary theory corresponds to the area of a minimal or quantum extremal surface in the bulk. Change the entanglement structure on the boundary and the bulk geometry adjusts accordingly. Remove entanglement and the bulk space-time fragments. This relationship becomes vivid when explored through tensor networks. Tensor networks are mathematical constructions used to efficiently represent highly entangled quantum states. They consist of nodes connected by links, where each link represents entanglement between subsystems. When such networks are arranged in particular patterns, they reproduce many geometric features expected of space-time. In these models, spatial distance corresponds to the number of entanglement links separating subsystems. Regions that share many entanglement bonds appear close. Regions with few shared correlations appear far apart. The geometry is not imposed. It emerges from the structure of the quantum state itself. Space-time becomes a way of visualizing entanglement connectivity. This perspective explains why the entropy-area relationship feels fundamental rather than accidental. Area counts entanglement links crossing a boundary. A surface with larger area corresponds to more entanglement connecting the regions it separates. Entropy scales with area because entanglement does. From this vantage point, the black hole interior becomes a region defined by entanglement rather than classical enclosure. The island prescription fits naturally. When the entanglement structure reorganizes, regions that once belonged to the interior become part of the radiation's entanglement wedge. Geometry follows correlations, not the other way around. One of the most striking expressions of this idea appears in the ER equals EPR conjecture, proposed by Leonard Susskind and Juan Maldacena. The conjecture equates two concepts that previously belonged to different domains. ER refers to Einstein-Rosen bridges, geometric wormholes connecting regions of spacetime. EPR refers to Einstein-Podolsky-Rosen pairs, quantum systems linked by entanglement. The conjecture proposes that these are two descriptions of the same underlying phenomenon. According to ER equals EPR, entangled systems are connected by non-traversable wormholes at the level of quantum geometry. These wormholes do not allow signals to pass through. They preserve causality, yet they encode the entanglement structure geometrically. Entanglement becomes the glue that holds space-time together. This conjecture reframes wormholes from exotic solutions of Einstein's equations into natural expressions of quantum correlation. A wormhole need not be engineered or stabilized. It can arise as a geometric representation of entanglement between subsystems. In this sense, space-time connectivity becomes synonymous with quantum connectivity. Black holes provide the most dramatic testing ground for this idea. A black hole horizon marks a region of extreme entanglement. Degrees of freedom just outside the horizon are strongly entangled with degrees of freedom just inside. That entanglement maintains the smoothness of spacetime across the horizon in semi-classical descriptions. As evaporation proceeds and entanglement shifts from interior modes to radiation, the geometric picture evolves. The interior becomes increasingly encoded in correlations among distant radiation quanta. In holographic language, the entanglement wedge of the radiation grows to include regions that once lay behind the horizon. The geometry adjusts to reflect this redistribution. From this perspective, black holes act as entanglement machines. They absorb information, rapidly scramble it across horizon degrees of freedom, and then re-express it through long-range correlations in outgoing radiation. The process transforms localized information into highly non-local entanglement. Geometry tracks this transformation. This view also clarifies why information recovery appears so difficult. The information is not hidden behind a classical barrier, it is dispersed into correlations spanning vast numbers of degrees of freedom. Reconstructing it requires decoding an emergent geometric structure built from entanglement. The difficulty lies in complexity rather than obstruction. The firewall puzzle appears differently as well. If spacetime smoothness arises from entanglement, then preserving a smooth horizon requires maintaining appropriate entanglement patterns. The island mechanism and holographic encoding suggest that these patterns can change without forcing violent local effects. Geometry reorganizes itself as correlations redistribute, allowing unitarity and horizon smoothness to coexist in subtle ways. In this framework, space-time ceases to be fundamental. It becomes an emergent language for describing how quantum information is organized. Distances, interiors, and horizons reflect patterns of correlation rather than independent physical ingredients. Gravity emerges as the effective dynamics governing these patterns at large scales. Black holes sharpen this lesson because they push entanglement to its limits. They maximize entropy for a given energy. They scramble information as efficiently as quantum mechanics allows. They convert simple inputs into complex global correlations. Their geometry reflects this extremal behavior. Seen this way, the information paradox transforms once again. It no longer asks how information escapes a region bounded by geometry. It asks how geometry itself arises from and responds to quantum information. The paradox dissolves into a question about emergence rather than loss. Space-time emergence from entanglement does not provide a final theory of quantum gravity. It provides a direction. It suggests that understanding gravity requires understanding how quantum systems encode correlations at scale. Black holes serve as the clearest demonstration that geometry, entropy, and information are inseparable. The remaining task is to translate this insight into a complete dynamical framework, one that explains how classical spacetime emerges from quantum structure in ordinary settings, and how extreme configurations like black holes reorganize that structure without contradiction. By this stage of the discussion, the phrase information recovery can easily mislead. It evokes an image of signals escaping a black hole, messages being reconstructed, or data being pulled back out in some operational sense. In the modern understanding, information recovery means something far more precise and far more constrained. It is a statement about the structure of quantum states and their evolution, not about practical retrieval by observers. In quantum theory, information is considered recovered if the final state of a closed system retains a one-to-one correspondence with its initial state. This correspondence exists at the level of the global wave function. It does not require that an observer can efficiently decode or interpret the information. It requires only that no two distinct initial states evolve into the same final state. Recovery, in this sense, is theoretical rather than operational. This distinction matters because black hole evaporation pushes practical accessibility and theoretical preservation far apart. Even if information is preserved in principle, the physical effort required to extract it can exceed any realistic capability. Quantum mechanics allows states to be information complete while remaining computationally opaque. The difficulty arises from complexity rather than obstruction. As a black hole scrambles information, it distributes correlations across an enormous number of degrees of freedom. Each emitted quantum carries only a tiny fraction of the global structure. The correlations that encode the original information are non-local and extremely high order. Reconstructing them requires global access to the radiation and the ability to perform collective operations whose complexity grows exponentially with system size. This exponential growth defines a complexity barrier. It is not imposed by fundamental law. It emerges from the structure of unitary evolution in chaotic quantum systems. The decoding map exists, yet implementing it requires resources that scale beyond any feasible limit. The information remains present, but functionally unreachable. This situation mirrors familiar phenomena in quantum many-body physics. A system can evolve unitarily and preserve information while rapidly thermalizing. After thermalization, local observables reveal little about the initial state. Reconstructing that state demands control over microscopic correlations across the entire system. Black holes represent the most extreme version of this behavior. Importantly, this form of inaccessibility does not violate causality. No signal travels faster than light. No observer receives information before it could have been emitted. The release of information through Hawking radiation occurs only after the black hole has had time to scramble and emit correlated quanta. The Hayden-Preskill analysis respects these constraints exactly. Recovery times exceed scrambling times and include delays associated with emission and propagation. The absence of causal violation highlights a common misconception. Information recovery does not mean that information escapes directly from behind the horizon. It means that the quantum state describing the radiation eventually contains correlations sufficient to encode the information that once described the black hole interior. The encoding is indirect, distributed, and delayed. Geometry enforces causal separation. Quantum correlations enforce consistency. This distinction also clarifies the difference between loss and scrambling. Information loss refers to a many-to-one mapping in time evolution, where distinct initial states converge onto an identical final state. Scrambling refers to a one-to-one mapping that spreads information into degrees of freedom that are difficult to access. Loss violates unitarity, scrambling preserves it. Black holes scramble information maximally. They take simple inputs and convert them into correlations that involve essentially every available degree of freedom. From the standpoint of local measurements, the result resembles loss. From the standpoint of the global quantum state, the information remains fully encoded. The island framework reinforces this interpretation. When fine-grained entropy calculations show that the radiation purifies itself after the page time, they demonstrate that information is present in the radiation as a whole. They do not provide a practical decoding procedure. They establish existence, not accessibility. This separation resolves a long-standing confusion in the paradox. The paradox arose because thermal radiation appears featureless and random. Randomness suggests loss. Quantum theory distinguishes between randomness arising from ignorance and randomness arising from complexity. In black hole evaporation, the apparent randomness reflects the latter. Information recovery, then, does not contradict the experience of observers. No observer collects Hawking radiation and reconstructs a star. No violation of thermodynamic intuition occurs. Entropy increases locally. Radiation looks thermal. The arrow of time remains intact. What changes is the global accounting. In this sense, black holes respect every operational constraint while still obeying quantum law. They preserve information without advertising it. They obey causality without simplifying reconstruction. They align with thermodynamics without destroying unitarity. The phrase information recovery therefore names a consistency condition, not a physical process that observers witness. It asserts that the universe keeps its records even when it renders them unreadable. The difference between loss and scrambling lies at the heart of this understanding. Black holes do not forget. They entangle, disperse, and complicate. The information remains present, encoded in correlations so elaborate that practical recovery fades from relevance. What survives is not memory in the everyday sense, but consistency in the quantum one. By the time the information paradox reaches this point, the original question has shifted. It began as a challenge to memory itself, whether black holes erase the past. It ends as a redefinition of what memory means in a quantum universe governed by gravity. The modern view no longer treats black holes as exceptional failures of physical law. It treats them as extreme but lawful quantum systems. In this view, a black hole is a unitary quantum object. Its formation, evolution, and evaporation are governed by quantum dynamics that preserve the one-to-one mapping between states. The horizon does not mark the end of information. It marks a transition in how information is stored and expressed. What falls in becomes encoded in degrees of freedom that are highly entangled, rapidly scrambled, and non-locally represented. Information does not vanish, it redistributes. Matter collapsing into a black hole brings with it quantum correlations, phase relationships, and state distinctions. These distinctions do not remain localized. They spread across horizon degrees of freedom, then across Hawking radiation, then across correlations linking radiation emitted at vastly separated times. The process replaces locality with entanglement as the carrier of memory. This redistribution explains the deceptive simplicity of black holes. Externally, they appear bald: mass, charge, angular momentum. Internally, and in the quantum description, they are maximally complex. Their simplicity reflects coarse graining. Their memory resides in correlations that ordinary measurements cannot resolve. Semi-classical intuition fails precisely because it was never designed to track fine-grained quantum information in a dynamical space-time. Treating geometry as fixed and computing local radiation captures energy flow and approximate thermality. It misses global correlations that become relevant only when entropy accounting is performed carefully. The paradox emerged not because semi-classical gravity was wrong, but because it was asked a question beyond its scope. Quantum extremal surfaces and islands demonstrate where the correction lies. Entropy in gravity depends on which degrees of freedom are included in the subsystem, and that inclusion can change with time. The boundary between inside and outside becomes state-dependent. Geometry itself participates in the bookkeeping. Once this is accepted, the apparent contradiction dissolves without violating any tested principle. The implication for quantum gravity is profound. Space-time geometry no longer appears fundamental. It emerges from quantum structure. Horizons, interiors, and distances reflect patterns of entanglement rather than immutable background features. Gravity becomes an effective description of how quantum information organizes itself at large scales. Black holes expose this structure because they push it to an extreme. They maximize entropy for a given energy. They scramble information at the fastest allowed rate. They convert simple initial states into correlations of overwhelming complexity. In doing so, they reveal how deeply information and geometry intertwine. The information paradox reshaped modern physics because it refused to stay local. It linked thermodynamics, quantum mechanics, general relativity, complexity theory, and geometry into a single problem. Attempts to resolve it forced new tools to be developed, from holography to quantum error correction to gravitational path integrals with replica wormholes. Each advance clarified that information was never truly missing. It was misaccounted. In the end, black holes do not forget. They transform memory into a form that resists intuition. They trade accessibility for consistency. What survives is not a readable record, but a conserved quantum structure that guarantees reversibility at the deepest level. The paradox did its work by revealing the limits of familiar concepts. Memory ceased to be a localized thing. Space ceased to be a container. Horizons ceased to be simple boundaries. What replaced them was a picture in which information defines structure, entanglement defines geometry, and gravity emerges as a large-scale consequence of quantum law. Black holes stand as the clearest demonstration that the universe keeps its books perfectly, even when it hides the ledger.